Welcome to the first session of the lecture on the rectangular waveguide called the rectangular waveguide 1. Here we will investigate the construction of the potential functions for the rectangular waveguide, for the rectangular waveguide modes. We will investigate the dispersion equation for the rectangular waveguide. We will investigate the dispersion equations for the rectangular waveguide, the cutoff frequency and the dominant mode, and the propagation characteristics of the TE and TM modes in the rectangular waveguide. Let us go to the lecture. We had previously constructed the electromagnetic field solutions for two cases. One, when the magnetic vector potential was A equal to u z psi, and another when the electric vector potential was F is equal to u z psi. These are the two cases for which we had constructed the field solutions, and we found that for this case where the magnetic vector potential was z directed, it gave rise to a transverse magnetic to z mode, that is a mode the mode for which H z equal to 0. The z directed magnetic field was 0, and for this case the solution came out to be TE to z, for which the z directed electric field was 0. When we now apply this knowledge to any kind to analysis of any guided mode behavior in a waveguide, the first thing we need to understand is that whether these are valid mode sets in the rectangular waveguide, whether these modes are indeed valid modes for the rectangular waveguide. These modes, whether they are supported in the rectangular waveguide. So, for that purpose we need to take the field expressions for these modes, the Tm to z and the Te to z, and we need to satisfy the boundary conditions of the waveguide. If the boundary conditions are properly satisfied and adequately satisfied by the Te to z or the Tm to z modes, we simply conclude that those modes are valid mode sets for the waveguide. If they are not, these mode sets are not valid mode sets for the waveguide, and we have to continue to hunt for alternative mode sets. And in the context of the rectangular waveguide, the only alternative mode sets are two other mode sets, where A will be equal to u y psi and F will be equal to u y psi, or A equal to u x psi and F is equal to u x psi. We already discussed those things before. But let us assume that we are lucky and these kinds of potential functions, which is A equal to u z psi and F is equal to u z psi, will indeed be valid mode sets in the waveguide. We think they would be, but we are not sure. In order to better substantiate our claim and be sure that the T to Z and the Tm to Z mode sets are valid mode sets in the waveguide, we now need to satisfy the boundary conditions of the waveguide. We also know that in a rectangular waveguide, the transverse electromagnetic mode, the TM mode, we know that the transverse electric magnetic mode or the TEM mode does not exist, because the waveguide does not have a central conductor. So, the TEM mode does not exist in the rectangular waveguide. So, now let us see whether the Tm to Z mode is a valid mode in the waveguide. The waveguide is bounded by conducting walls. On all 4 sides. So, this is the waveguide. Let us call this direction x, this direction y. So, this direction will be z, and let this dimension be a and let that dimension be b. If we would look at the z component of the electric field for the TM to Z mode, the TM to Z mode does not have a Hz component, because the magnetic fields because the magnetic field will only have Hx and Hy. So, the TM to Z mode has the Ez component along the z direction only. So, if I write down the expression for the electric field for the TM to Z mode, it will be Ez equal to y cap 1 by y cap, it will be Ez equal to 1 by y cap del square plus del z square plus k square psi, and that is equal to 1 by y cap minus k z square plus k square psi. So, this electric field E z will have to vanish at all 4 walls of the rectangular waveguide. So, we will have to satisfy the boundary conditions E z is 0 at x equal to 0, x equal to a, y equal to 0 and y equal to b. Because of the nature of the boundary condition along x and along y, this can only happen if the variation along x and y is given by a sinusoid. So, we have if the potential function is expressed by h k x x, h k y y with the propagation term along the z direction being given by e to the power minus j k z z. Let us call this equation number 42. Maintaining continuity with our previous equation numbers, there was one gap with respect to the magnetic current, some of the equation numbers for the magnetic current, but that will not create a confusion because those equations are already given with a different equation number in another slide. So, you would be able to refer to those equations whenever you need them. So, because of that there is a gap in equation number here, but that should not cause any confusion. So, this refers to the x variation of the potential function, this refers to the y variation of the potential function, and this is the z variation of the potential function. So, h k x x has to be given by sin k x x in this case with k x given by m pi by a. M equal to 1, 2, 3. Similarly, h k y y is given by sin k y y, where k y equal to n pi by b, where n equal to 1, 2, 3 and so on. So, therefore, the psi function for the Tm to Z mode, that is transverse magnetic to Z mode, will be given by psi mn Tm to Z as sin m pi x by a So, the psi function corresponding to the Tm to Z mode or the transverse magnetic to Z mode will be given by sin m pi x by a sin n pi y by b e to the power minus j k z z, that is 43, where m is 1, 2, 3 and n is 1, 2, 3. Also, the separation equation which we wrote down before, in this case becomes k square is k x square plus k y square plus k z square, and that is given by m pi by a whole square plus n pi by b whole square plus k z square. So, if we substitute this psi function into the equations for the electric and magnetic field we derived corresponding to A equal to u z psi, which corresponds to the Tm to Z mode, we will obtain all the electric and magnetic field components corresponding to the Tm to Z mode. So, just substituting this psi function to the electric and magnetic field components we derived for this case, which involve the psi function, we just substitute the psi function in those equations, we will get all the electric and magnetic fields corresponding to the Tm to Z mode for the rectangular waveguide. For instance, if we need to find out the E y component, which is given by 1 by y cap del square psi del y del z for the Tm to Z mode for the substitution A equal to u z psi, we need to just perform these two differentiations. So, it will be n pi by b for the differentiation with respect to y sin m pi x by a cos n pi y by b e to the power minus j k z z multiplied by minus j k z. Okay, whatever that is. So, this is an example of how the Ey component of the electric field for the Tm to Z mode for the rectangular waveguide can be obtained. Okay. So, we will substitute 1 by y cap, the value of y cap, and we will just simplify. Now, let us consider the fields that are transverse electric to Z. We got or we obtained the expressions for the Te to Z mode by the substitution f equal to u z psi. There we found that E z was equal to 0, which corresponds to the Te to Z mode. So, we pick up those fields and we substitute we pick up those fields and we apply the boundary conditions of the waveguide and see whether it is possible to satisfy the boundary conditions of the waveguide using those field expressions. Because there is no z component of the electric field, we have to use the Ex and the Ey components of the fields. So, writing down the Ex and Ey components of the fields, we have Ex equal to minus del psi del y, which must vanish. This must vanish at y equal to 0 and y equal to b. Similarly, we have Ey as del psi del x, which must vanish at x equal to 0 and x equal to a. This can only happen if h k x x, which we defined before, the x variation of the psi function, that is equal to cos k x x with k x as m pi by a, m is equal to 0, 1 and 2, because we are dealing m equal to 0, 1, 2, 3 and so on, because we are dealing with the cosine function, we have m equal to 0 also as a choice. And h k y y will be given by cos k y y with k y as n pi by b with n equal to 0, 1, 2, 3 and so on. However, the fields vanish if m and n are both 0. So, therefore, we cannot have m and n both 0. M and n cannot both be simultaneously 0. M and n cannot both be simultaneously 0, otherwise the fields vanish. So, therefore, the psi function for the m nth mode corresponding to the transverse electric to z field is given by cos m pi x by a cos n pi y by b e to the power minus j k z z. We call this as equation 45, where m equal to 0, 1, 2, 3 etc. and n equal to 0, 1, 2, 3 etc. But m equal to n equal to 0 is not allowed. Now, the separation equation which we wrote down for the T m to z mode, which is k square equal to m pi by a whole square plus n pi by b whole square plus k z square, it is the same in this case. So, the same separation equation k square is m pi by a whole square plus n pi by b whole square plus k z square holds good. So, therefore, note that for both the T m and T e modes k z depends on m and n. That means, the propagation constant along the z direction depends on the mode number and of course, the frequency, because k will depend on frequency, k is given by omega root mu epsilon. So, it will depend on the mode number and the frequency. Also, if the frequency is very high, so k is very high in that case. So, there k z will be very high and it may be these two terms m pi by a whole square plus n pi by b whole square for a sufficiently high frequency may be neglected or may be small for a sufficiently high frequency. So, as the frequency becomes very high, k z approaches the propagation constant in free space, which is k. So, the propagation constant in the waveguide approaches that of free space or the propagation constant in a homogeneous medium filled with the same media parameters as that of the waveguide for a sufficiently high frequency. So, similar to the TM to Z mode, the expressions for the electric and magnetic fields for the TE to Z mode can be obtained by substituting this psi function into the equations for the electric and magnetic field that were derived or that were given before for the case f is equal to u z psi, because this choice generates the TE to Z mode. So, substituting this psi function into the electric and magnetic fields corresponding to f equal to u z psi, we obtain the electric and magnetic fields in the waveguide for the TE to Z mode. So, let us write this equation as to explicitly show its dependence on frequency. Omega square mu epsilon plus m pi by a whole square. So, let us write this equation in order to show its explicit dependence on the frequency as omega square mu epsilon equal to m pi by a whole square plus n pi by b whole square plus k z square. So, we now see also that corresponding to the frequency omega c, corresponding to omega c square mu epsilon equal to m pi by a whole square plus n pi by b whole square, k z becomes equal to 0. So, k z becomes equal to 0 means the propagation along the z stops. There is no propagation along the z direction. So, omega equal to omega c, for which omega c square mu epsilon equal to m pi by a whole square plus n pi by b whole square, the frequency omega c is called the cutoff frequency below which the propagation constant becomes complex. So, we write k c square equal to omega c square mu epsilon, that is equal to m pi by a whole square plus n pi by b whole square, corresponding to the case k z equal to 0. Defines the cutoff frequency or the cutoff condition for the waveguide. So, when omega is less than omega c, k z becomes complex and the wave is attenuated or the wave is called evanescent. So, omega c is twice pi f c. So, which corresponds, this is the radian cutoff frequency, this is the cutoff frequency in hertz or gigahertz. So, as we said that below the cutoff frequency the mode is evanescent and above the cutoff frequency the mode propagates. Particularly above cutoff k z is real, it is beta, and that is given by root of k square minus m pi by a whole square minus n pi by b whole square. And below cutoff, k z is minus j alpha we have to choose minus j alpha and not plus j alpha, because the variation along the z is e to the power minus j k z z. So, if we choose minus alpha if we choose k z equal to minus j alpha, it becomes minus j times minus j alpha z, and that is equal to e to the power minus alpha z, which represents attenuation. So, this represents attenuation. So, had we made the other choice, had we made the choice k z equal to plus j alpha, this wave e to the power minus j k z z would have corresponded to minus j into plus j alpha z, that is e to the power alpha z. So, which represents wave increase along the z direction, which is not possible. So, we forsake this choice. So, below cutoff, we have k square as m pi by a whole square plus n pi by b whole square minus alpha square. So, therefore, alpha is given by, or that attenuation constant, root of m pi by a whole square plus n pi by b whole square minus k square. So, we call this equation 47. As we also wrote before, the cutoff frequency is given by omega c square mu epsilon is m pi by a whole square plus n pi by b whole square. And from which f c is given by 1 by 2 root epsilon mu root of m by a whole square plus n by b whole square. We call this 48, where omega c equal to twice pi f c. So, the cutoff wavelength is given by lambda c equal to c by f c is equal to 1 by root of epsilon mu f c. And that is given by two by root of that is given by that is given by 2 by root of m by a whole square plus n by b whole square. The dominant mode, which is the mode corresponding to the lowest cutoff frequency, it corresponds to the lowest cutoff frequency, is given by m equal to 0, n equal to 1. So, if m equal to 0, it has a uniform, if you derive the equations for the fields for the electric and magnetic fields for the TE to Z mode, or in this case the TE 01 mode, which is the dominant mode. If I again draw the cross section of the waveguide, so this is the x axis, this is the y axis, this is A and that is B. That is B. So, the electric field will only have a Ex component, and the magnetic field will only have a Hy component and Hz component. For the T01 mode. The electric field is going to be maximum here and it is to so the electric field is going to be maximum here and it is going to be 0 at the two edges of the waveguide, because the tangential fields at y equal to 0 and y equal to b, they will be 0. So, this is the electric field distribution of the T01 mode. The TM01 mode will be degenerate to the TE01 mode, in the sense that it is going to have the same cutoff frequency as the TE01 mode, but however, the fields of the TE01 mode are 0. So, therefore, the TM01 mode do not exist. That is fortunate for us, because had it existed, its field components would have been very different from the TE01 mode, because the fields of the TEMN mode is very different from the fields of the TMMN mode. But it must be remembered that the TEMN mode is degenerate with the TMMN mode. It means that the TMN mode and the TEMN mode and the TMMN mode have the same cutoff frequencies. Why? Because this equation is independent of whether the mode is TE or TL. Also, its propagation characteristics, which is kz, the value of kz, as defined through here, or for the TM mode, or as defined through here for the TE mode, they are the same. So, kz will be also the same for the TEMN and the TMMN mode. So, we call this degenerate. Okay. But because the TM01 mode does not exist, the TM01 mode does not exist. So, the dominant mode is only the TE01 mode. The field distribution again of the TE01 mode has a uniform field, has a uniform strength of the field along the x direction, because the field strength is invariant along the x, because the variation along the x is 0. So, we always want to maximize what we call the monomode bandwidth of the waveguide. For any guided structure, we want to maximize the monomode bandwidth, that is the frequency gap between the dominant mode and the onset of the next higher order mode, because that is where we like to have because that is where we want to have propagation, because after the onset of the next higher order mode, we will have two modes propagating. So, the two modes are going to share power. Therefore, we want the propagation to happen in what we call the monomode region, that is between the cutoff frequency of the dominant mode and the cutoff frequency of the next higher order mode. Okay. So, this concludes our first slot of the waveguide characteristics. We will continue with other characteristics of the waveguide. We will continue with other characteristics of the waveguide. Thank you.